Welcome to our fifth press conference at the AAS 224th meeting. Today's press conference, morning press conference, will be in Astronomical Oleo, and we have four speakers speaking on various subjects. Curtis DeWitt of the University of California, Davis is going to speak about first light with the Echelon cross-shell spectrograph from SOFIA and some of the first discoveries, observations it made. Then Brian Williams from NASA Goddard Space Flight Center is going to talk about some results from Spitzer, Type 1a supernova with a circumstellar interaction, and Kepler's older cousin, perhaps. And I believe that refers to the supernova remnant itself, not Kepler. It's not a... Yes, so we're talking about the 1604 supernova and a remnant that resembles it. Then Galaxies on Fire. Stellar feedback explains inefficient star formation in galaxies. Philip Hopkins from the University of California at Berkeley will talk about some new Caltech now. Okay, so things change. These are numerical simulations that he's going to discuss that show us how galaxies formed. And then the first spectroscopic confirmation of a monster galaxy at redshift 3.3, as by Cemile Marsan of Tufts University. As usual, we'll hold the questions till the end. We'll start with Curtis, and then questions will be after all our four speakers. Thank you.
So reset button.
Just press reset.
Okay. Good morning. I'm Curtis DeWitt. I'm from the University of California, Davis, and I'm part of the team that made first flight with the EXES instrument on the SOFIA aircraft. And I'm going to talk about how this opens up a new window to the universe in observing molecules in mid-infrared radiation. EXES flies aboard SOFIA, and I'll give a brief background of SOFIA. This is NASA's Airborne Observatory, which is a 2.5-meter telescope that's borne aboard a heavily modified 747 aircraft. At high altitudes, a sliding door opens up and the telescope collects light from the universe and focuses it down to one of 6 very specialized astronomical instruments. EXES is the youngest of this suite of instruments, and the reason that EXES is unique is twofold. The first is that our view of mid-infrared radiation from the universe is nearly completely blocked by our own atmosphere and the molecules in it. So when we try to observe molecules from the universe, our own molecules get in the way, and the way to get around this is to fly above 99.9% of, that would be the Earth's water vapor in the atmosphere. But all molecules similarly are reduced at this high altitude in their interference with what we see from the universe. And you can see the view in the top panel here has all this patchy stuff that we can't see through, and in the bottom panel we can see nearly 90% of the light from the universe, allowing us to look at molecules for the first time. The other reason that EXES is unique with SOFIA is because of what EXES does with the light. We take a relatively narrow slice of the spectrum, we put it through our dispersing optics and split the colors into precision so that we can see color differences of 1 part in 100,000 of the wavelength. And it basically gives us a barcode of chemical signatures from molecules in space, identifying what exactly we're seeing and what the conditions of and the physics around those molecules are. And this is enabled by the technology within EXES, which is a very large aluminum bar grating, which is called an echelon grating. And it's 130 precisely machined mirrors in a staircase pattern that splits the light into what you see in the right panel here, and giving us this ability to see chemical fingerprints from the universe. So the reason this capability hasn't existed until now, we've been above the atmosphere, we've seen these wavelengths before, but we've never seen it at these resolutions, is because EXES is such a very heavy object in order to split light into so many so finely into different colors. It's about 1,000 pounds, and nobody's thought to put it on a satellite before. Well, a 747 very easily lifts 1,000 pounds into the stratosphere, so we've been able to take advantage of this and see things that haven't been seen before. Our flights were in April 2014, so just 2 months ago, and one of the things we were most excited to go out and get is to look in these chemical factories in the surrounding regions of protostars. This is a spectrum of the protostar in Cygnus X called AFGL 2591. It's a 10 solar mass star that's just 1 million years old and still encased in a cocoon of gas and dust from which it formed. And this cocoon is what we're interested in because there's so many, this is a factory for making water and other molecules, and the star itself is lighting that up for us to see and see the constituents in those chemical barcodes and all the processes that are going on in really splendid detail. The other scientific highlight, we observed Jupiter in molecular emission from hydrogen. And what this tells us is about the vertical mixing in the atmosphere of Jupiter because of lines that EXES has access to but weren't previously viewable. And what it also tells us is that even on an object as well studied as Jupiter, there's new things to be found in this new capability and ability to see molecular radiation. So this was just with a few hours of flight and in our first test flights on EXES. And there's a bright feature with EXES to view other things that have molecules in space like comets, more protostars and protostellar cocoons, atmospheres of cool stars, and atmospheres of our own solar system planets. So I think I'll end here.
There we go. All right, good morning. I'm going to talk about, I changed my title to a more exciting title. It's going to be Raising the Dead, and that'll become clear what that means later on, and challenging what we know about how Type 1a supernovae explode. I am Brian Williams. The reporter's in the room. I'm simply the other Brian Williams, not this imposter that's running around. We all know that Type 1a supernovae are important in astrophysics. They've allowed us to calibrate the expansion of the universe and discover dark energy and all sorts of wonderful stuff. These guys got prizes for doing that. The thing is, we don't actually really know how these things explode in the way that we know how core collapse, the more massive star supernovae explode. What we do generally agree on is that it must involve the explosion of a white dwarf star. And a white dwarf is simply a star that's, about the size of the Earth. It's a burned out dead star. It's what the sun will evolve into in a few billion years. We call it a degenerate star. Not because it's poorly behaved, but just because of the physics that go on inside of it. What we generally agree on is that this star must be in a binary system with another star. What we don't actually know, though, is what is that other star. So there's sort of two competing models here. The first one is the one that people might actually be more familiar with. This is one where you have a white dwarf star and a companion star that's a more normal star. It could be a red giant star, it could be an AGB star, it could be a sun-like star. And what would happen in this case is the more massive companion would dump matter onto the white dwarf star, and when the white dwarf reaches a certain point of instability, it would explode. This, for a long time, was the favored model. I'm not even that old, but even a decade ago when I was in grad school, this was pretty much all we learned. This was how it must be. A second model, though, has come into favor, and that's that we actually have two white dwarfs that orbit around each other and somehow spiral in and collide or merge or do something, and magic happens, and then you get an explosion. In the past 5 to 10 years, this has actually become the more favored model of the two. And in fact, studies have been done that suggest that 80 to 90 to maybe 100% of Type 1a supernovae may actually be this type, and maybe everything that we learned before about the single degenerate model was wrong. Some people have referred to the single degenerate model as being dead, and maybe the double degenerate model is the only model that can make these Type 1a supernovae. We don't actually know because it's hard to, we've never yet imaged a system before it explodes and after it explodes. So we're all looking at indirect evidence here, unlike the massive star supernovae where occasionally we can actually see a star before it explodes and then after it explodes, and we know exactly what it was. So we have to look for indirect evidence, and there's a lot of indirect evidence we can look for. The one that I'm going to talk about in this talk is that the single degenerate model might, under the right circumstances, produce a lot of mass loss before the supernova. So you might have this star just blowing off a dense stellar wind for thousands or millions of years before the thing explodes. The model with two white dwarfs shouldn't have this because there's no obvious way that two white dwarfs can blow a stellar wind. I mean, by definition, they're dead stars, so they're not doing anything like that. So if we can see a type 1a supernova go off into a dense medium, it might be evidence that we have a case of a single degenerate explosion. Well, this is, people have tried to do this from supernova observations with some success. It's a difficult observation to do. What I actually do is look at the supernova remnants. And so we use the Spitzer telescope to observe dozens of supernova remnants. And the one that caught our eye in particular was this little guy. So this guy's phone number is 0509-68.7. His friends call him N103b. It's that little red blotch in the center there, and I've blown it up so you can see what it looks like. This caught our eye for several reasons, mostly because when we looked at the spectrum of this thing, we saw something that we don't normally see in these objects. We saw an awful lot of dust that was very hot and very dense. And it was, in fact, an order of magnitude or more denser than any other type 1a supernova we've ever seen, with the exception of one, which I'll point out in a second. And in fact, when we did the models and modeled the spectrum, we found that there must be several solar masses of material that had been dumped off prior to the explosion of this supernova, that the shock wave from the supernova is now running into. And that's what we're seeing now in this spectrum. I mentioned we've seen this one other time. The only other time we've ever seen this is in Kepler's supernova, which is a pretty famous object in our galaxy. Kepler is the remnant of the supernova of 1604 AD, and in the past 5 years or so, work by a lot of different groups, myself, other collaborators and colleagues around the world have shown that Kepler seems to also have this. It seems to also have this very dense circumstellar medium around it. And by the way, these are out to light years. These aren't like right around the star. These are things that have been blown off for millions of years before the star exploded. Just to show you how alike these things are, here's the spectrum from N103b and Kepler plotted on top of each other. The blue one is Kepler, the green one is N103b. The separation between them is entirely arbitrary. I just scaled it up by 50% so they didn't lie right on top of each other. It's really a remarkable similarity between these two. And these are the only two of the dozens of type 1a supernova remnants that we've seen. These are the only two that have ever shown this. So in conclusion, we have N103b, which is about 1,000 years old. We don't have an exact date on it, but we can bracket it pretty well. We know it's the remnant of a type 1a supernova, and it seems to have a dense circumstellar medium around it. What that implies is that we may have another case, like Kepler, where we actually have a single degenerate explosion. And so while it may very well be the case, and in fact I actually believe that most type 1a supernovae in the universe are probably from the double degenerate model of two white dwarfs, we may still have a case where this model is still viable. Another way to put that is a single degenerate channel is not all dead. At worst, it's mostly dead, but mostly dead is not all dead. And finally, among type 1a remnants, I said these two are the only roads where we have this. But since N103b is a few times older and significantly larger than Kepler, my colleagues and I have taken to calling it Kepler's older cousin. So I will end there. Thank you.
So we're going to change gears a little bit, and I'll be the theorist in the group, which means I get to say anything I want is my interpretation of that. I'm Phil Hopkins. I'm at Caltech, and I want to talk to you guys about a project I've been leading for the last few years involving a large number of collaborators across the UCs and also Northwestern that we're calling the FIRE Project for Feedback in Realistic Environments, and hopefully I'll explain what that actually means. This is an example of the kind of numerical simulations that are coming out of this project. The first results are out, and there's about 5 more papers staged to come out over the next month or two. If you want more details, this is our project website, fire.northwestern.edu, and I'd encourage you to check it out if for no other reason than to download the really cool movies. What do I mean when I say inefficient star formation? Well, if you ask me, the most important and fundamental unsolved problem in both galaxy formation and star formation is why are there so few stars? Contrary to popular belief, it's not actually hard to form a star. The hard part is why don't we form everything into stars? Why don't we form stars everywhere all the time super fast? It's actually really hard not to form stars. And that's always where the models fail. So this is just one example of it. If you ask what's the mass function of galaxies, what's the number of galaxies as a function of their number of stars, which is what's plotted here, number of galaxies versus the number of stars in the galaxy, the white curve is what we actually see, and this blue curve here is what you'd predict if you put in the simplest theorist's model. You'd say, I understand gravity, I understand chemistry that allows the gas to lose energy, that sort of thing. And I'm just going to say at some point when it's sufficiently dense, it's eventually going to turn into a star. And that's inevitably what you predict is a line like that. It doesn't look anything like what we see. And a more intuitive way of looking at this is what's plotted here, same information content. But what I'm plotting is the fraction of the baryons, the normal matter, inside of a dark matter halo, inside of the bound, gravitationally bound dark matter component of a galaxy that's actually been successfully turned into stars as a function of the mass of that system. And the white line is, again, just what we see, and the blue line is what this naive model predicts, which is basically all of it. You predict that all the normal matter should be locked up in stars, or at least half of it. And there's about a factor of 10 discrepancy at the mass of the Milky Way, but for small and big galaxies, that grows to a factor of 1,000 or so discrepancy between what we see and what we think. So, being theorists, we want to approach this, and this is a complicated problem, so you have to use numerical simulations because there's so many different physics involved in explaining this process. So, this has been something people have been working on for a long time, trying to put these physics into a simulation and follow a galaxy from the beginning of the universe to today. But there have been some serious limitations. So the state of the art in most of the field, including up to today, for example, the physics in the illustrious simulation, which is one recent example that's gotten a lot of attention, and I've worked with the people on that project actually, reflects the present state of the art. And this is a movie of what a galaxy disk in gas looks like with the present state of the art before this project. And the resolution is typically something like thousands of light years. So a large fraction of the galaxy is one resolution element, or 1 billion solar masses. And at that resolution, you can't resolve structure in the interstellar medium. So you just say the gas in a galaxy is a single, idealized fluid. It sort of behaves like honey because of purely numerical reasons. And it ends up looking like this illustration here. And you can see there's no interesting structure in the galaxy. And to the extent that there's winds coming out of the galaxy, since you can't resolve that structure, you can't model those winds sort of a priori. So you just say, by hand, I have to fiat that there are winds. So I say, for every star I form, I throw out something times that mass in a wind. And that's how I make galaxies expel winds. So how can we do better? Well, through a heroic coding effort and physics effort by the collaborators in this project, I think we've been able to tremendously improve on this and really bring things into the next generation of simulations. So, if you'll excuse the cheesy transition, how does this compare to what we're trying to do in this project? Well, we're trying to push the resolution to the point where we can resolve qualitatively different physics. So, our resolution can now reach something like 1 to 10 light years, smaller than the sizes of molecular clouds in which stars are actually forming, or thousands of masses and solar masses in stars. And this is what you get in that kind of a simulation for the structure of the gas in a galaxy. You can see immediately you form this very complicated multi-phase structure. And there's a lot of new physics that go into resolving that. It's not just about increasing resolution for the bragging rights. It's that allows you to follow faithfully the chemistry in the cold and warm phases of the gas, the interaction of radiation from stars with matter, and the interactions of supernovae with that matter. And you can see what happens is you form this multi-phase turbulent medium in which the dense regions collapse and form stars, but then a combination of the radiation from those stars and the supernova explosions blow up those dense regions, form these hot yellow bubbles that when you saw edge on end up building up until they vent out. They break out of the disk and launch these galactic winds that escape the galaxy entirely. And that just keeps going in sort of a very complicated steady state for as long as you evolve it. So this is what that looks like when you put it into a cosmological context and we follow a galaxy from the beginning of the universe to today. So this box just shows the gas on the right and the stars on the left in a galaxy about the size of the Milky Way today, followed from very early times. So this is redshift counting down. So at very early times, the universe was very homogeneous and smooth, and you saw that. And then it very quickly develops this structure. And what you can see very obviously is that that formation is incredibly violent, especially in these early times. It's violent in terms of what's falling into the galaxy, but it's also violent in terms of what's coming out of the galaxy. When the galaxy starts forming stars, these stars explode as supernovae, push on the gas with their radiation, and launch these huge outflows. And the gas is labeled by the temperature, so the outflows are coming out both in superheated gas at millions of degrees, but also in cold molecular and atomic gas being swept up and launched out of the galaxy. And the galaxy is launching often many, many times its mass in stars out. And finally, it's only at late times now that we see things start to calm down. The universe slows down in its expansion, gas sort of slows down in how fast it's dumping onto galaxies. In turn, the rate at which it can turn into stars slows down, and thus the rate at which stars are punching back on the medium slows down. So everything slows down, calms down. The galaxy gets kind of boring and middle-aged and doesn't want to go out anymore. So it just settles down and has a fairly quiescent late-time history here, where it forms these beautiful disks that we're used to seeing in our local universe, like the Milky Way. And then it has a party crasher come in at the very end to mix things up. So quantitatively, what does that do? Well, this is just showing that same plot I showed at the beginning of how inefficient star formation is. And the remarkable thing is, when you start putting these physics actually into the simulations and resolving how these interactions change the medium in which stars are forming, you really can start to explain why there are so few stars. So this is showing the mass in stars in a galaxy versus in dark matter. And the dotted line shows what I said before was the old theoretical prediction that everything should turn into stars. The green shows you what has actually observed, and the points are the results of all these simulations. The picture is just there to be pretty. It's a picture from one of the simulations. But you actually start forming realistic galaxies, both in how they look and in how massive they are. And one of the exciting things that's come out of this is not just that we vindicated this sort of 40-year-old idea that this impact of stars back on the medium can explain this discrepancy, but also that it's a lot more complicated than we previously imagined. In particular, for the people who care about the details, it turns out it's not just supernovae, it's not just radiation, it's not just wind from stars, but it's very much about the interaction between those mechanisms. And the last thing I'll show is just a preview of what's about to come out. One of the other exciting things that comes out for free from this kind of study are quantities that tell you about the dynamics of galaxies and maybe even about the structure of dark matter. So for a long time, it's been known that if you measure the density of dark matter as a function of the distance from a galaxy's center, and you look in small galaxies, the prediction from these old models was always this blue line that's steeply rising towards the center. The observations always showed a deficit of dark matter in the centers of galaxies. It was the outskirts where they needed lots of dark matter to explain the rotation curves. But in the centers, the models always predict too much dark matter. So we predict cusps instead of cores. Some people call it the too big to fail problem. It's been called various crises in cosmology before. But people had speculated that maybe all that's happening, instead of the dark matter model being wrong entirely and our having to go back to our cosmology, maybe what's happening is all these explosions are pushing the material around, and the dark matter gets kicked around to the point where it's not in this steeply concentrated distribution anymore. And in fact, that's what we see in these new results, and that's what will be in a paper by Jose and Yorbe very shortly. And this is just another movie showing one of these very tiny galaxies forming, just to give you an idea, again, of the violence of these explosions. And those explosions throwing all that material out of the galaxy means that the gravitational potential changes rapidly, and thus the distribution of dark matter gets kicked around. So, unfortunately, I don't think what we're seeing is exotic new dark matter physics, which would have been super exciting. What we're seeing is physics of stars that we haven't previously understood. All right, so to conclude, this project is just getting started, but we've pushed to the highest resolution cosmological simulations ever to follow galaxies all the way to today. And what's important about that, as I said before, is really that this lets us follow individual supernovae and radiation, really lets us see new physics that we weren't able to see in previous simulations. And that seems to have broken this long-standing logjam of understanding why galaxies form so few stars. And for the first time, we haven't had to put in that result by hand. We haven't had to tune things to get that answer to come out. So that's really, really exciting, and we are looking forward to exploring a lot of the other consequences of this. For example, whether this resolves existing problems that people have raised with the cold dark matter model. We think it can explain some. I don't know about others yet. Thank you.
Hello, everyone. My name is Cemile. I'm from Tufts University. I'm a graduate student. Today, I'll be talking about the first spectroscopic confirmation of a monster galaxy at redshift greater than 3, also known as a monster galaxy killed by a supermassive black hole. Okay, so I'll briefly begin by talking about the galaxies that we observe in the local universe. Basically, you can broadly classify them into 2 morphological groups. Here I'm showing Hubble's galaxy classification scheme. On the left we have elliptical galaxies, which are spheroidal in shape, and on the right we have spiral galaxies, which are flattened disks with spiral arms, hence the name. However, the bimodality is not restricted to morphology. The intrinsic properties of these galaxies are also different. Elliptical galaxies are the most massive galaxies that we observe in the universe. They are no longer forming stars. Spiral galaxies have ongoing star formation. So immediately a question arises, how did these different kinds of galaxies form? What are the physical processes that are responsible for shaping these galaxies? My main research topic is looking at the evolution of the most massive galaxies that we observe. So here, to begin addressing this question, we can look at the demographics of galaxies at different times in the cosmic time. So here I'm showing the number density of galaxies as a function of their stellar mass, which is on the x-axis. So if we look at the leftmost panel, which is the stellar mass function for today, the colored points are observations. The dashed and dotted lines are predictions from galaxy evolution models, and the red vertical line is the mass of the Milky Way, just for comparison. So for today, the leftmost panel, it looks like we have a good idea, but as we start looking at earlier in the age of the universe, we see that there's some discrepancies, especially at the high redshift, where when the age of the universe was 1.5 billion years old, we see that there's way too many very massive galaxies that are not predicted by models. Okay. Oh, yeah, sorry. So I'm looking at these very massive monster galaxies when the age of the universe was less than 2 billion years old. These are very rare objects, so we need large fields of sky to be observed in order to find these. And when they are found in images, we need confirmation spectroscopically. Today, I'll be focusing on the follow-up study of one of these monster galaxies. I gathered data from the largest telescopes in the world, looking at spectra, which is basically how much light is coming from a galaxy at different wavelengths. Here's a 2-dimensional spectrum, 1-dimensional spectrum, which is kind of around a specific transition line of ionized oxygen. And we can calculate how far away this galaxy is by looking at this spectroscopy. And how far away this galaxy is kind of a probe of the cosmic time at which we're observing this galaxy. That's when the age of the universe was 1.8 billion years old, which is 12 billion years ago. What else do we know about this galaxy? Its stellar mass is greater than 200 billion times the solar mass, which is 4 times more massive than the Milky Way 12 billion years ago. Its age of the stars in this galaxy is 400 million years, which means that most of the stars must have formed in a very short and intense burst of star formation. We also find indications of an active supermassive black hole in the center of this galaxy. So what is the role of active supermassive black holes on the evolution of galaxies? Energy and radiation that is generated when mass is being accreted onto the central massive black hole can literally just sweep gas out of the host galaxy. And gas is what fuels star formation, what you need for star formation. So when you don't have gas anymore, star formation is terminated. We can't really image these at high redshifts because they're too small, but here I'm showing in the local universe the Perseus cluster in the X-ray, and you can see that there's bubbles literally because the supermassive black hole is just pushing gas away. And in the bottom image is the ripples of pressure. So what does this mean for evolution of massive galaxies? So in the local universe, we have massive elliptical galaxies that are no longer forming stars. When the age of the universe was roughly 1 billion years old, we have very massive galaxies that are very violently forming stars. So what is a transition? What is halting star formation? It looks like we have the answer in this one object, which is kind of going through a post-starburst phase with indications of an active supermassive black hole, which could be potentially responsible for halting star formation. So in summary, we spectroscopically confirm for the first time a very massive galaxy when the universe was 1 billion years old. It must have formed as stars in a very short but intense burst of star formation. There's evidence of an active supermassive black hole, which is responsible for shutting off its star formation. And this galaxy is the progenitor of the most massive galaxies in the local universe, which is in the phase of transitioning into a post-starburst galaxy. Thank you.
We'll now take questions from the audience. Please speak in, wait for the microphone. Inga will be holding it. And identify yourself and the person you're asking a question to.
Sure. Chris Crockett, Science News. Question is for Brian Williams. This is probably a really stupid question, but with the supernova, how do we know it's type 1A a thousand years after the event?
No, that's actually a good question. It's sometimes hard to tell from supernova remnants, especially since we can't often see the actual explosion itself. When we look at supernova remnants, usually in the X-rays, we can do a pretty good job of typing them based on what sort of materials the star made. This one was long suspected to be a type 1A from the X-ray spectra from Chandra, and that's been published for 10 years now. The actual confirmation of this, I have to give credit to a colleague of mine, Armin Rest, who actually detected the light echo from this supernova. So we actually did detect the light bouncing off something else and coming to us now. And he is working on a paper now, but he gave me permission to use it in my paper, that it was matched the spectrum of a type 1A supernova.
Just follow up, is he also able to see the light curve of it too?
I'm not sure. You'd have to ask him. I think he just gets a snapshot, but the snapshot is the spectrum of the supernova itself. But I don't know any more than that.
Other questions from the audience? This one over here.
Daniel Castro from MIT. So this is a question for Brian, just following on that same question. How do the X-ray spectra compare between 0509 and Kepler? I mean, do they look as similar as what you showed us?
Yeah, they look fairly similar. I wasn't involved with the X-ray work for 0509, so I'm not as familiar with it as some other people are, but I think they actually look fairly similar. I mean, there's a lot of, you see a fair amount of iron in the ejecta, a lot of silicon, things like that. Not an overwhelming amount of oxygen, although you do see some. So it looks fairly similar.
Nola Red, freelancer. Sorry, this is a question for Brian. I was wondering, are there other potential causes for the spectral signature that you're seeing other than this sorry, I'm blanking today, other than the type 1A supernova? Like, is there something else that could be causing that same signal?
You mean the spectrum that I showed up
Yes.
here from Spitzer? I mean, I guess what you're asking is there an alternative explanation for it being some dense material that's been thrown around there? Yeah, I mean, you could imagine it just being some random chance coincidence with some very dense cloud that happened to be right next to the supernova at exactly the right time. It's possible. We think that's the more unlikely of the two scenarios. But you know, what we definitely see, the spectrum tells us that it is a lot of dense material around the supernova, and even from the X-ray spectra from Chandra, we have indications that that is indeed the case. So, I mean, yes, you can always come up with alternative scenarios, but we think they're fairly unlikely.
Other questions from the audience? Yes.
This is for Phil and Cemile. So, Cemile, you showed a very early, very large galaxy, and I was just wondering if the cosmological simulations that Phil was starting to do created those sorts of early, large galaxies.
Well, it's a good question. You're calling us out on where the current simulations fail. So the simulations we've done have mostly focused on galaxies smaller than and up to as big as the Milky Way. And observations like this are really exciting because I think I've been very interested in this question of what supermassive black holes do to galaxies. And the current generation of simulations, we put a lot of work into the physics of the interstellar medium and into what stars do to the medium, but we haven't yet caught up in putting in as faithful a treatment of what black holes do to the medium. And I think as a direct consequence of that, when we simulate the most massive galaxies in the universe, more massive, sort of off the plots to the right of what I was showing, we get them wrong. It's pretty clear that we need something else in those galaxies to be turning them off. So I think we probably do form enough stars early, but we know that we form way too many stars in general in those very most massive galaxies, even with the impact of stars back on the medium. So I wouldn't regard that as a good prediction for this kind of object existing. So the theory still has catching up to do there, and we just understand so much less about how black holes impact the medium than how stars do, how stars evolve, and that sort of thing. So I don't know if you wanted to add to that.
This is why I'm studying these very massive galaxies, actually.
Additional question? Maybe a follow-up for that for Cemile. You mentioned that the stars were all 100 million years old or so. How do you know that? Is it from the colors or what?
From spectral energy distribution modeling, basically, from the UV to all the way to the near infrared, basically.
We have a question from the web, I guess?
No, but from me, Rick Feinberg, AAS press officer. This is for Cemile also. How did you actually find this galaxy? You mentioned that, you know, in order to find rare objects, you have to look over large areas of sky, but you've only found one. How did you zero in on the haystack so that you could find the needle? Were you looking at known clusters, or were you looking at newly discovered clusters, or were you just looking where other galaxies, you know, or you know, what drew you to this field that ultimately led to success in finding this galaxy?
Well, I specifically did not find this galaxy. This galaxy was found in the Near Medium Band Survey, which is it's in the cosmos field, so it's a well-studied field. And what the Near Medium Band Survey kind of added to the existing data is that with the use of medium bands, we were able to find a better constraint on photometric redshift of these galaxies. So we kind of had a better idea of how far away it actually was. And we could actually, you know, go in with the telescope time and we were pretty sure that it was there to begin with, and then got the telescope time, basically.
What does medium band mean in this context?
Medium band means using a filter with a bandwidth that is not so wide. So you are able to sample the spectral energy distribution better than broadband photometry.
So a few a few tens of nanometers as opposed to hundreds of nanometers, or?
About like 150 angstroms is the width of the medium bands, roughly.
I think we're still on the cusp of angstroms and nanometer
Yeah.
usage. I'm always converting in my head. Other questions?
Always keep some in reserve. Rick Feinberg, AAS Press. This one's for Curtis. Kind of an unfair question, I suppose, but we've all heard that Sophia is threatened with being mothballed next year, and I'm just wondering, how does this affect real people? You guys have just started commissioning an instrument. You're getting exciting results. You've got a lot of potential, and then you find out that you may lose your ride up into the stratosphere. Tell us a little bit about, if you're willing, about how the team reacts to this kind of thing, and what it means for scientists who are trying to, who have spent a lot of time building an instrument and are now just getting it underway, yet face the possibility that it'll be just taken away.
Well, this isn't a dodge of the question, but when we shipped our instrument down there and a day later heard the news about the president's budget, and so it put pressure on us because we thought that, we considered that it was maybe the only flights that EXES would ever get, but there would still be like great opportunities in just those 2 flights. So it put the pressure on, but we didn't really think too far ahead because there was just no time to wonder how we got in this position and for self-pity and that kind of thing. And I'm happy with how it looks like it's being resolved right now because with this extra time, the observatory can have a real legacy.
I have one other question for Brian again. You mentioned, what is there in the signature of that spectrum that tells you right away that you're looking at a dense medium? Is it a strong infrared continuum, or what?
Yeah, it's basically the shape of the continuum tells you the temperature of the dust. And the temperature of the dust is an indicator, a direct indicator of the gas density. Basically, the denser the gas, the hotter the dust will be. Mm-hmm. And those 2 spectra that I showed from Kepler and N103b are by far the hottest we've ever seen.
So if we, my thought was, scientifically speaking, for the audience, it would have been nice to see a couple of the spectra that didn't match.
Yeah, I thought about that.
Clearly different.
I'm fairly certain one of my collaborators even suggested putting that in, but I didn't want to go over the 7-minute slide limit. I can refer you to papers, and I can certainly show you the differences. I don't have any on me, but yeah, they're
quite a
if
different
anyone
shape.
really doesn't believe me, I will be happy to refer you to papers. But trust me, it looks different. Those 2 are in a class by themselves.
No other questions? We will refer you to personal contact with these speakers if you'd like to ask some questions after the press conference, and we thank you very much for a great job and hope you'll all write it up. One other announcement before we close. We are having a seminar this afternoon rather than a formal press conference, but this will be, first of all, on the expanding universe of shrinking satellites. And as with a number of these seminars which we've started to have, this may point the way to future press conferences and future articles, so we hope you'll all attend. Thanks very much. 2:15.